All right. So f of c has to be defined. So if you plug in whatever the c value is, you should get a defined value for y. The limit has to exist, right? The function has to have a limit that exists at that c value. So it's sort of, well, it's definitely implied that it's from the left and from the right if you're doing it visually. Algebraically, it's a plug and chug kind of situation. Also, whatever the defined value is, that has to coincide with whatever the limit is at that point. All right, so that's a weird one because you would think, well, when would it not be that? And there's a pretty good example of when it would not be that. Extreme close-up. Whoa. So you have a function. It would look something like this, with an open circle. All right, so this would be not continuous. We'll call this point C at C. All right, so that's an example. You know, it's not the only one, but it's an example of item 3 there. All right, so you're looking at a case where a point is defined at C. That would be the closed circle. The limit exists. The paths are approaching this open circle. So the limit would be whatever the y value is at that open circle. The issue is 1 and 2 don't coincide with each other. Right, so you don't get the same result for both parts. That's what number 3 is talking about. All right, so pretty important. All right, continuity on an open interval. A function is continuous on an open interval a to b if it's continuous at each point along the interval. A function that is continuous on the entire real line, negative infinity to infinity, is everywhere continuous. Right? Everywhere continuous, continuous everywhere means the same thing. On a closed interval, that's really addressing what we were talking about above. It's just basically saying that you're not limited to an infinite domain, right? That's a weird thing to say. But you're on a set finite interval. And from that finite interval, can you determine continuity, right? In which case you'd be looking at the endpoints. You'd be looking at the limits coming in from the left and from the right. Right? So we'll take a few minutes and go through a couple of examples so you get the hang of it. And then we'll look at a practical application. It's all going to seem very familiar, I think, but it has a little bit of a limit twist to it. So f of x equals the square root of 1 minus x squared. 1 minus x squared under a radical, I would want to make sure that that's a non-negative entry, right? I want that to be greater than or equal to 0. All right, we can factor. We can use common sense. We can use a graph. A lot of different possibilities. You can just, if you want, it's a binomial. Subtract the 1. Get negative x squared greater than or equal to negative 1. Divide x squared less than or equal to positive 1. And then take the square root. Right? So we would say x is less than or equal to plus or minus 1. Plus or minus x is equal to 1. Or, I'm sorry, less than or equal to 1. You could say the absolute value of x is less than or equal to 1. That's a nice way of representing it in a concise fashion. It's allowing for that plus or minus relationship. Also, that's telling us that we're looking at an interval that would be between negative 1 and 1. All right. So definitely a closed interval. This is not something that would be everywhere continuous. You know that based on the fact that there's a radical there for the most part. It could have been everywhere continuous if it was a plus sign in the middle, but that's not the case. So the question would become, on this particular interval, are we looking at something that is continuous? So on this closed interval, right? So that's where this funny business is going to come into play. What I need to justify my answer, so in a rigorous calculus approach, extreme close-up, whoa. I need the limit as x approaches -1 from the right of f of x. And I need the limit as x approaches +1 from the left of f of x. And I just need to show that they exist. Doesn't matter what they are, they just need to exist. All right. The idea is, and forget about what the actual graph looks like. Just draw something arbitrary. I know I'm looking at, here's -1, here's +1. You got something like that. That's not even remotely like what that graph looks like, but just use your imagination. If that were the case, by solving this algebraically, we've determined that the interval from -1 to 1 is fine, because that's the solution that gives values that are greater than or equal to 0. The only points that would be of any concern would be the points at the end. So if I can show that going to -1 from the right exists, and that going to 1 from the left, if that exists, then I'll show that on this interval we're looking at a function that is continuous. All right? So in a lot of cases it's just algebra. In this case, it is just that. So -1, pop it in, you get something that exists, right? And it also, you know, it's kind of determined through the algebra anyway. So 0 in both cases, right? All right, so these exist. So we're looking at a function that is continuous. So therefore, f of x is continuous on the interval of -1 to 1 with brackets. All right. This whole limit process was really only to determine whether I'm throwing brackets or parentheses around this interval. Right? Because, you know, you could have something, for example, I'll give you a case where you would have parentheses. If this were 1 over the square root of 1 minus x squared, then by going through the algebra to solve 1 minus x squared greater than or equal to 0, you would get anything on the interval of -1 to 1, but then you would realize, oh, wait a minute, it can't be greater than or equal to 0. 0 would make it undefined. So we would find the limit going out to -1 from the right and 1 from the left, and show that that equals to something undefined, right, in which case we throw parentheses around it. All right, so it's really not bad. It just seems like a total waste of time. And I respect your opinion on that. It's not something I would want to do either. But for some reason, the College Board is very concerned with your ability to do stuff like that. All right, determine the intervals on which the function, probably should have read it before, is continuous. So let me rewrite the function as sine of x over cosine of x. All right, in which case, I would just want to know values of x that make cosine equal to 0. All right, that happens where? When's cosine equal to 0? X equals 0 would give us a 1. Pi halves, yeah. Then, what's the other one in the 0 to 2 pi interval? 3 pi over 2. And then if we were allowed to go around again, it would be, so 1 pi over 2, 3 pi over 2, 5 pi, 7 pi, and so on. All right, separated by half circles every step of the way. What's half circle in radians? Pi, right? So we do plus pi k. Where k is an integer. Where k belongs to the set of integers. On my tests, if you say just plus pi k, you're fine. On the College Board exam, you know, the AP. If you don't tell them what the k represents, they're not giving you full credit. Because k could be anything, and if you don't stipulate that it's specifically integers, then you're in trouble. All right, so that gives us all the values for which the function is undefined. So we were making the assumption that it's continuous everywhere else. Right, so what I would need to do, I'm just going to do a quick sketch. So let me get a pi over 2 and a negative pi over 2. Get those asymptotes in there. Draw the tangent function. All right, so what I would need to do here is find the limit as x approaches negative pi over 2 from the right of f of x, and the limit as x approaches pi over 2 from the left, also f of x. Visually, we could just make the determination that it's going to negative infinity as we approach negative pi over 2 from the right. It's going down forever. And go into positive infinity as we go to the right. So, how would you do that analytically? We'll talk about that down the line. We need to know about derivatives first. And there's a technique called L'Hopital's rule that's going to help us with stuff like this. All right. Other techniques also, improper integrals and things like that. Well, at least when we get to integration. So anyway, this is telling us that at least when we're focusing on this one curve, that we would not include the bounds. All right, so it's continuous. On the interval of negative pi over 2 to pi over 2. But I want to replicate that interval infinitely. So I want to allow for this to happen again and again and again this way, again and again and again that way. So what I'm going to do is I'm going to translate the lower bound and the upper bound by pi units. So the way to address that would be just to say plus pi k where k belongs to the set of integers. All right, so it's moving the entire interval rather than a single point. Question?
Yeah, I have a question. How come in the beginning we were looking for something to make cosine x equals 0? Like, I just don't understand that first.
Because we want to find where it would be discontinuous, because we know everywhere else it'll be continuous.
Okay.
And so that told us that we would have cutoffs at negative pi over 2 and pi over 2. So I would know on the interval in between I'm looking at something that's continuous. So I'd make a statement about that, allowing for the fact that I could never get to the negative pi over 2 or pi over 2. So basically counterexample. We're always looking for the counterexample or examples.
If you find the limits on each end, there still could be a discontinuity like in the middle. So
True.
How do you know?
That would have been fleshed out in the algebra.
Okay.
So you would have seen that when you looked at the original function. A case, I only focused on the case where it was undefined, but if there was a radical in there or a common factor or something like that, I would have noticed it early on, and that would have worked itself out. All right, so for B, we're looking at, well, something kind of funny, I guess. You have the sine of 1 over x, which is definitely undefined when x is equal to 0. You don't have to do any algebra for that. But they're excluding it here. So that's wonderful. They're filling in the origin in the second piece of the piecewise function. It's just a question of whether or not the whole or the discontinuity for the first piece happens to be at 0, 0. We know it's at an x value of 0, but what's the y value that corresponds to that? So what we need to figure out is the limit as x approaches 0 of the sine of 1 over x. All right. Which would be another left-hand, right-hand side limit kind of situation. All right. So what I would do, or at least until we learn something called the Squeeze Theorem, is just take a look in the calculator. We'll learn, we'll have a little bit of a payoff for this analytically sooner rather than later. So it's not one of those where you have to wait like 3 months to see how to do it by hand. You just gotta wait a day. So sine of 1 over x. I'll just do a zoom trig, zoom 7. All right, so we have that. If you go into your table, well, let's change it to 0 and 1. See, you have an error at 0. It's just a question of will that error converge on 0 itself? So is this y, if I actually decrease my increments for x, will this start to approach 0 from the left, and will that start to approach 0 from the right? If that's the case, then we're looking at something that's continuous, because if the hole is specifically at 0, 0, then this would plug the hole. But if it's not a hole, then this isn't going to plug anything. All right, so we can flesh it out using the calculator, center it around 0, make this really small. Delta table goes down very small. All right, so maybe it seems to be bouncing back and forth between a negative, positive and a negative number. Same idea on the other side. Go even smaller. I didn't memorize the exact number that came in the last iteration of this, but I think it was smaller than that. I think it was like 0.35. And this is now 0.48, which is not getting closer to 0, it's getting further away. So that's my suspicion. So it's 0.48. Let's see if it's getting closer to 0 as I make this more extreme, or if it's getting further away. Well, that didn't help. I overchecked. Let's go like, I'll go 12. Maybe 11. All right, well, this kind of proved my point, although I'd like it to have a little bit more accuracy. The calculator has a hard time with oscillating discontinuities, but basically what it's telling us is that it's not converging on 0, because it was at, for a larger delta x, it was at a smaller y value prior to the error. So as I decreased my change in x, the y value got larger. So I mean, it's not taking off like an exponential function or anything like that, but it is getting away from 0, not closer to 0. All right. So yeah, and you can kind of get a sense of that visually. So zoom 7 to get the graph, and then maybe like a zoom box. That's assuming you don't want to do any thinking about the domain. So enter in the upper left-hand corner. Down and over, enter. When you create a field around the graph. It seems like it's developing more funk in the middle than previous. And you can also do a zoom in and then recenter your cursor. All right, so it's getting crazier and crazier the more that you zoom in. So this is not something that's definitely converging in terms of a hole or something like that. All right, so the limit would not exist. All right, so this function is not continuous everywhere. It has a discontinuity of some kind at 0. Right? Just because there's a point here doesn't mean that it coincides with what this is. Right? So we're saying continuous on the interval of -infinity to 0, exclusive of the 0, and then 0 on. And, you know, a pre-calc question almost always would have the excluded value getting filled in by the other piece of the piecewise function. Here, not necessarily the case, so you do have to flesh it out. Now, like I said, later on I'll show you how to find this limit by hand. It involves some funky technique, but we're not there yet. So one that's very similar, but not exactly the same. So same idea though, I have to set it up by finding the limit as x approaches 0 of x times the sine of 1 over x. We'll see what that looks like. Calculate early. So zoom trig. Maybe. I'll box it in, zoom box. Create a box around the interval that you want, domain and range. Does it go through the origin? Maybe. It's hard to tell. So 0, I'll start with something more reasonable. That looks like it's really close to 0, and so does that. All right? If you're unsure, you can kind of go a little crazier with it. And see. It looks like it's getting more extreme, but that's really tiny. All right? So that looks like it's closing in on 0. All right? And again, different story for a different day. I'll show you how to figure it out by hand, but for now we can say that the limit is going to approach 0. All right, so here we're looking at something that is everywhere continuous. In fact, evidence suggests that absolute 0 cannot be attained. How did scientists determine that 0 Kelvin is the lower limit of temperature of matter? What is absolute 0 on the Celsius scale? All right, so we have two pieces of information here. One of which is the temperature. And the V represents volume of a gas, of a particular gas. All right, we're looking at a relationship here that is, it's seemingly linear, but you don't really notice that until you kind of flesh it out. What we're really looking at is a direct relationship where one variable increases, so does the other. And it does seem to be at a pretty consistent rate. And it's not like you're increasing by 1 or 2 here and then 10, 20, 30 down the line. It's consistently around 1 or 2 units. Right? And in terms of t-values, we're increasing at a particular rate. So what we could do, if you wanted to, you could do a linear regression in your calculator. But this one is actually, you know, spoiler alert, it's kind of designed for you to do it by hand. So you could find the slope, for example, which I'll do here. All right, so change of y over change in x. We're going to have a difference of 20 for the quote-unquote x variable. The other one I think I need a calculator for. 5, 6. No, 1.7. All right, so 1.6426. Assuming I typed it in correctly. Divide by the 20, so the change in the y over the change in the x. Math bracket on the off chance that it comes up with a nice neat fraction. It does not, but you never know, so you give it a look. So 0.08213. All right, so we're looking at a linear function, v equal to 0.08213 times t plus a y-intercept. A convenient one is this guy, because it has the x value or the t value of 0. So pop that on at the end, 22.4334. All right, so that's a relationship between the two variables. It's a linear relationship. I didn't verify this for you on paper, but it is a true statement that if you chose any of the two coordinates, you'd still get the same slope. All right, that's not a guarantee. Sometimes it's a quadratic relationship. Maybe it's a trig relationship. In this case, it does work out to be linear. All right, so what we would want is to determine a limit, right? I wouldn't want to find the limit as the temperature approaches 0 of the volume, because that's not really, that's not what we're looking for. I want to find the lower limit of temperature. So what I would want to do is determine, as my volume is getting closer and closer to 0, what the temperature would end up being. All right, so in order to do that, I have to solve this for t in terms of v. So t equals v minus 22.4334 over 0.08213. So then as an extension, or at least continuation, I'd be looking for the limit as v approached 0 of my function t of v. Now, if we're looking at 0 being an absolute measure, the absolutely lowest value that you could possibly have. For temperature, yeah, that's the goal, but for volume, then you couldn't find the limit coming in from the left. That wouldn't make any sense. You can't start off with a negative volume, right? So we would necessarily have to be coming in from the right. So to have the proper notation, it would have to be approaching 0 from the right. The good news is, since we're looking at a function that doesn't have a discontinuity of any kind, we're in good shape because it's just plug and chug anyway. So from the left, from the right, if you're dealing with a continuous function, a function that's everywhere continuous, and I didn't flesh this out algebraically, but we can just take note of the situation. This is a linear function, right? What we did was we solved for the independent variable, basically finding the inverse of the linear function, right? Or something that if we were to graph it with reverse variables would be the inverse. Inverse of a linear function is a linear function. Linear functions are everywhere continuous, right? So you don't have to justify that. If I plug in a 0 for v, I'm going to get negative 22 point blah, blah, blah over 0.08213. Which is going to give us negative 273.145. Degrees Celsius. So if we know that there's a linear relationship between temperature and volume of some piece of matter, then, and we have that relationship to fall back on, then we would know as the volume approaches 0, your temperature should be approaching its minimum value. Right? So what we got from this is that the lowest possible temperature of matter would be negative 273.145 degrees Celsius, which hopefully, assuming I didn't screw something up, is the Celsius equivalent of 0 degrees Kelvin. All right, so that's actually where that conversion comes from. All right, so it's pretty cool. All right, so you're going to do all of this stuff for homework, which seems like a lot, but it's not.